actively online on Twitch. Alright, looks like we're online. Do we have sound? Okay. Then I'll just begin. Chapter 21, Fields. It is natural to ask whether or not some field f is contained in a larger field. We think of the rational numbers, which reside inside the real numbers, while in turn the real numbers live inside the complex numbers. We can also study the fields between Q and R and inquire as to the nature of these fields. More specifically, if we are given a field f and a polynomial p of x and fx, we can ask whether or not we can find a field E containing f, such that p of x factors into linear factors over e of x. For example, if we consider the polynomial p of x is equal to x to the fourth minus 5x squared plus 6 in q of x, then p of x factors as x squared minus 2 times x squared minus 3. However, both of these factors are irreducible in q of x. If we wish to find a zero of p of x, we must go to a larger field. Certainly the field of real numbers will work, since p of x is equal to x minus square root of 2, x plus square root of 2, x minus square root of 3, x plus square root of 3. And as such, it is possible to, the field of numbers will work since we can split it into, like, real components, because the square root of 2 and the square root of 3 are not in our field naturally, in the rationals. It is possible to find a smaller field in which p of x is a 0, namely q adjoin the square root of 2 is equal to, oh gosh, give me a second, I just messed up my tabs. Q adjoin square root of 2 is equal to a plus b square root of 2, with a and b in the rational numbers. We wish to be able to compute and study such fields for arbitrary polynomials over a field f. So 21.1, extension fields. A field E is an extension field of a field f, if f is a subfield of E. The field f is called the base field, and we write f as a subset of E. So for example 21.1, for example, let f be equal to q adjoin square root of 2, and let E be equal to q adjoin square root of 2 plus square root of 3 to be the smallest field containing both q and square root of 2 plus square root of 3. Because E and f are extension fields of the rational numbers, we claim that E is an extension field of f. To see this, we need only show that square root of 2 is an E. Since square root of 2 plus square root of 3 is an E, 1 over square root of 2 plus square root of 3 equals square root of 3 minus square root of 2 must also be an E. Taking linear combinations of square root of 2 plus square root of 3 and square root of 3 minus square root of 2, we find that square root of 2 and square root of 3 must be an E. Example 21.2. We know that p of x is, p of x is equal to x squared plus x plus 1 is in z mod 2 of x. Since neither z nor 1 is the root of this polynomial, we know that p of x is irreducible over z mod 2. We will construct a field extension of z mod 2 containing an element a such that p of a is equal to 0. By theorem 17.22, the ideal p of x generated by p of x is maximal. Hence, z mod 2 of x over the ideal generated by p of x, yes, is a field. And this comes to the fact that, maximal ideals correspond to fields under their quotient rings. Let f of x plus the principal ideal of p of x be an arbitrary element of z mod 2x over p of x. By the division algorithm, f of x is equal to x squared plus x plus 1 q of x plus r of x, where the degree of r of x is less than the degree of x squared plus x plus 1. Therefore, f of x plus x squared plus x plus 1 is equal to r of x plus x squared plus x plus 1. The only possibilities for r of x are then 0, 1, x, and 1 plus x. Consequently, E is equal to z mod 2x over x squared plus x plus 1 is a field with 4 elements and must be an extension field of z mod 2, containing a 0a of p of x. The field z mod 2 of a consists of the elements 0 plus 0a is equal to 0, 1 plus 0a is equal to 1, 0 plus 1a is equal to a, and 1 plus 1a is equal to 1 plus a. Notice that a squared plus a plus 1 is equal to 0 in this case. Hence, if we compute 1 plus a squared, 1 plus a times 1 plus a is equal to 1 plus a plus a squared is equal to a. Other calculations are accomplished in a similar manner. We summarize these computations in the following tables, which tells us how to add and multiply elements in E. So we have 0, the addition table is just like the normal addition table as you would take with linear factors, except that everything is mod 2. So like a times a is equal to 0 and 1 plus 1 is equal to 0. But what's interesting is the addition table, in which case we have this very non-trivial structure, which is symmetric in these. The following theorem, due to Kronecker, is so important and so basic to our understanding of fields that it is often known as the fundamental theorem of field theory. So theorem 21.5, Let f be a field and p of x be a non-constant polynomial in f of x. Then there exists an extension field E of f and an element A in E such that p of A is equal to 0. So, I don't know if I'm going to write down the details yet. So, proof. To prove this theorem, we will employ the method that we used to construct example 21.2. Clearly, we can assume that p of x is an irreducible polynomial. If it's reducible, then the extension field f can just be f itself. We wish to find an extension field E of f containing an element A such that p of A is equal to 0. The ideal, the principal ideal generated by p of x, is a maximal ideal of f of x by theorem 17.22. Hence, f of x over the ideal generated by p of x is a field. We claim that E is equal to f of x over the ideal of p of x is the desired field. We first show that E is an extension field of f. We can define a homomorphisms of commutative rings by the map psi of f goes to f of x over the ideal generated by p of x, where psi of a is equal to a plus p of x for a and f. So we basically define it as a natural projection, treating it as an abelian group. It is easy to check that psi is indeed a ring homomorphism. Observe that psi of a plus psi of b is equal to a plus p of x plus b plus p of x is equal to a plus b plus p of x is equal to psi of a plus b, and psi of a psi of b is equal to a plus p of x b times p of b plus p of x equals ab plus p of x is equal to psi of ab. To prove that psi is 1 to 1, assume that a plus p of x is equal to psi of a is equal to psi of a, psi of b is equal to b plus p of x. Then a minus b is a multiple of p of x, since it lives in the ideal p of x. Since p of x is a non-constant polynomial, the only possibility is that a minus b is equal to 0, and consequently a is equal to b, meaning that psi is injective. Since psi is 1 to 1, we can identify f with the subfield a plus p of x of E and view E as an extension field of the new way we depicted the field f. It remains for us to prove that p of x has a 0 a in E. Set a be equal to x plus p of x, then a is in E. If p of x is equal to a naught plus a1x plus all the way to plus an x to the n, then p of a is equal to a naught plus a1 x plus p of x plus on and on to plus an x plus px to the n is equal to a naught plus a1 x plus p of x plus all the way to plus an x to the n is equal to a naught plus a1 of x plus on and on to plus an x to the n plus p of x is equal to 0 plus p of x. And therefore, we have found an element a in E equal to f of x over p of x, such that a is a 0 of p of x. Okay, let me double check this. Alright, so let set a to be equal to x plus p of x. A is in E, so if p of x is then that we wrote that, substituting it in the value, and just using the standard substitution methods, treating it as something over that field, gives us, yes, okay, that all checks out looking at that. Therefore we found an element of that form. Alright, example 21.6. Let p of x be equal to x to the fifth plus x to the fourth plus 1 in z mod 2 of x. Then p of x has irreducible factors x squared plus x plus 1 and x cubed plus x plus 1. For a field extension E of z mod 2 such that p of x is a root in E, we can let E be either z mod 2 of x over x squared plus x plus 1 or z mod 2 of x over x cubed plus x plus 1. We will leave it as an exercise to show that z mod 2x over x cubed plus x plus 1 is a field with 2 to the 3 equals 8 elements. So now, algebraic elements. An element A in an extension field E over F is algebraic over F if f of A is equal to 0 for some non-zero polynomial f of x in f of x. An element in E that is not algebraic over F is transcendental over F. An extension field E of a field F is an algebraic extension of F if every element in E is algebraic over F. If E is a field extension of F and A1 to AN are contained in E, we denote the smallest field containing F and A1 to AN by F of A1 all the way to AN. If E equals F of A for some A and E, then E is a simple extension of F. Okay, so there's a bunch of terminology and I'll probably be flashing back to this a bunch while we're reading this. So example 21.7. Both square root of 2 and I are algebraic over Q, since they are zeros of the polynomials x squared minus 2 and x squared plus 1, respectively. Clearly, pi and E are algebraic over the real numbers, However, it is a non-trivial fact that they are transcendental over the rationals. Numbers in R that are algebraic over Q are in fact quite rare. Almost all real numbers are transcendental over Q. So what this means is the probability that a real number chosen at random from the interval from 0 to 1 will be transcendental over the rationals is 1. I'm not going to explain how that works. Just trust me that I'm not going to bring the measure theory into this. Just trust me that makes sense. In many cases, we do not know whether or not a particular number is transcendental. For example, it is still not known whether pi plus e is transcendental or algebraic. A complex number that is algebraic over Q is an algebraic number. A transcendental number is an element of C that is transcendental over Q. So whenever we talk about things in relation to Q, we're talking about Q as our base field and C as our extension field. Example 21.8. We will show that the square root of 2 plus the square root of 3 is algebraic over Q. If a is equal to the square root of 2 plus square root of 3, then a squared is equal to 2 plus square root of 3. Hence, a squared minus 2 is equal to the square root of 3, and a squared minus 2 squared is equal to 3. Since a to the fourth minus 4a squared plus 1 is equal to 0, it must be true that a is a 0 of the polynomial x to the fourth minus 4x squared plus 1 is in Q of x. So for a lot of this, we basically can just reverse operation, and then set a polynomial there. It is very easy to give an example of an extension field E over a field F, where E contains an element transcendental over F. The following theorem characterizes transcendental extensions. So theorem 21.9. Let E be an extension field of F and alpha in E. Then alpha is transcendental over F if and only F alpha is isomorphic to F of x, the field of fractions F of x. So proof. Let phi of A from F of x to E be the evaluation homomorphism for alpha. Then alpha is transcendental over F if and only if phi of alpha, P of x, is equal to P of A is not equal to 0 for all non-constant polynomials P of x and F of x. This is true if and only if the kernel of phi of A is equal to 0. That is, it is true exactly when phi of A is 1 to 1. Hence, E must contain a copy of F of x. The smallest field containing F of x is the field of fractions F of x. By theorem 18.4, E must contain a copy of this field. We have a more interesting situation in the case of algebraic extensions. So theorem 21.10. Let E be a simple extension field of the field F, and alpha in E with alpha algebraic over F. Then there is unique irreducible monic polynomial, P of x in F of x, of smallest degree, such that P of A is equal to 0. If F of x is another polynomial in F of x such that F of A is equal to 0, then P of x divides F of x. So proof. Let phi of A to F of x to E be the evaluation homomorphism. The kernel of phi of A is a principal ideal generated by some P of x and F of x with the degree of P of x being greater than or equal to 1. We know that such a polynomial exists, since F of x is a principal ideal domain and alpha is algebraic. The ideal, P of x, consists exactly of those elements of F of x having alpha as a 0. If F of alpha is equal to 0, and F of x is not the 0 polynomial, then F of x is in P of x, and P of x divides F of x. So, P of x is a polynomial of minimal degree having alpha as a 0. Any other polynomial of the same degree having alpha as a 0 must have the form beta P of x for some beta in f. Suppose now that P of x is equal to R of x S of x is a factorization of P of x into polynomials of lower degree. Since P of alpha equals 0, R of alpha S of alpha equals 0, and consequently, because our polynomial is monic, either R of A is equal to 0 or S of A is equal to 0, which contradicts the fact that P is a minimal degree. Therefore, P of x must be irreducible, which in part, this comes from a combination of a bunch of things. For this last paragraph especially is the fact that a field is an integral domain. Let E be an extension field of F, and alpha be an E be algebraic over F. The unique monic polynomial, P of x, of the last theorem is called the minimal polynomial for A over F. The degree of P of x is the degree of A over F. Example 21.11. Let f of x be equal to x squared minus 2, and g of x equals x to the fourth minus 4x squared plus 1. These polynomials are the monic polynomials of square root of 2 and square root of 2 plus square root of 3, respectively. Proposition 21.12. Let E be a field extension of f, and alpha and E be algebraic over f. Then f of alpha is isomorphic to f of x over P of x, where P of x is the minimal polynomial of alpha over f. So proof. Let phi of A from f of x to E be the evaluation homomorphism. The kernel of this map is p of x, where p of x is the minimal polynomial of A. By the first isomorphism theorem, I should probably write this down. So we have evaluation from f of x to e. So we have the evaluation at alpha. And the kernel is generated by, let me double check what it is. This contains, yes, it's kernel. The kernel of phi of A is going to be not isomorphic, is going to be equal to the principal ideal generated by p of x. Considering every polynomial is that has A as a 0 is a multiple of this. So then just using first isomorphism theorem again gets us f of x over p of x. And since we have all the constant polynomials in this means that this function is surjective, which means we get a proper isomorphism here. And not only that, we actually also get a proper unique isomorphism, which is awesome. Alright, the kernel of this map is p of x, or like one that commutes at least. But first, let's put f now. Theorem 21.13. Let E be equal to f of A be a simple extension of f, where alpha in E is algebraic over f. Suppose that the degree of alpha over f is n. Then every element beta in E can be expressed uniquely in the form beta equals beta naught plus beta 1 alpha plus on and on to plus beta n minus 1 alpha n minus 1 for beta I in f. So what this is saying is that functionally we have a basis, or we have a kind of pseudo basis. We have the span of elements of the form a to the n, or a to the j. Yeah, so the set of elements a to the, that's g, a to the j for 0 is less than or equal to j is less than or equal to degree of a minus 1 actually spans the extension field. Excuse me, proof. Since phi alpha f of x is isomorphic to f of a, every element in E is equal to f of a must be of the form phi alpha f of x equals f of a, where f of a is a polynomial in A with coefficients in f. Let p of x be equal to x to the n plus a n minus 1 x to the n minus 1 plus on and on to plus a naught be the minimal polynomial of A. Then p of a equals 0. Hence, a to the n is equal to just like subtracting minus a n minus 1 all the way to minus a naught. Similarly, a n plus 1 is equal to alpha a n is equal to negative alpha a n minus 1 alpha n minus a n minus 2 alpha n minus 1 all on and on to minus alpha naught alpha, which is equal to, using the inductive step one more time, negative alpha n minus 1, negative alpha n minus 1 alpha n minus 1 and on to minus alpha naught, minus, and then you just apply the same thing again. So you're basically, once you have this identity, you just expand it out to like continually lower the identities. Continuing in this manner, we can express every monomial a to the m with m greater than or equal to n as a linear combination of powers of a that are less than n. Hence, any beta in f of a can be written as beta equals beta naught plus beta 1 alpha plus on and on to plus bn minus 1 alpha n minus 1. To show uniqueness, suppose that beta is equal to beta naught plus beta 1 alpha plus on and on to plus beta n minus 1 alpha n minus 1 is equal to c naught plus c1 alpha plus on and on to plus cn minus 1 alpha n minus 1 for bi and ci and f. Then, g of x is equal to b naught minus c naught plus b1 minus c1 x plus on and on to plus bn minus 1 cn minus 1 x to the n minus 1. And this is in f of x with g of alpha equals 0. Since the degree of g of x is less than the degree of p of x, the irreducible polynomial of a, g of x must be the 0 polynomial. Consequently, c naught, b naught minus c naught is equal to b1 minus c1 is equal to on and on to equal to bn minus 1 minus cn minus 1 is equal to 0. Or b sub I is equal to c sub I. Therefore, we have shown uniqueness. Oh my god, it's so cool. It's so cool. I love this. I don't know if you can tell by my tone of voice, but this is just, this is so good. This is so good. Alright. Example 21.14. Since x squared plus 1 is irreducible over R, x squared plus 1 is a maximal ideal in R of x. So, E is equal to R of x over x squared plus 1 is a field extension of R that contains a root of x squared plus 1. Let alpha be equal to x plus x squared plus 1. we can identify E with the complex numbers. By proposition 21.12, E is isomorphic to R alpha is equal to A plus B alpha, with A and B in R. We know that alpha squared is equal to -1 in E, since alpha squared plus 1 is equal to x plus x squared plus 1 squared plus 1 plus x squared plus 1 is equal to x squared plus 1 plus x squared plus 1 is equal to 0. Hence, we have an isomorphism of RA with C defined by the map that takes alpha A plus B alpha to A plus BI. Let E be a field extension of a field F. If we regard E as a vector space over F, then we can bring in the machinery of linear algebra to bear on the problem that we will encounter in our study of fields. The elements in the field E are vectors. The elements in the field F are scalars. We can think of addition in E as being vectors. When we multiply an element in E by an element in F, we are multiplying a vector by a scalar. This view of field extensions is especially fruitful if the field extension E of F is a finite dimensional vector space over F. And theorem 21.13 states that E equals F of A is finite dimensional vector space of F with basis 1, alpha squared, all the way to alpha n minus 1. So what we do is basically, I'll write all this down. So if F is a subset of the extension field E, then we define a product from F times E to E as Fe is equal to Fe. It's weird to write, but it's technically Fe goes to Fe if we want to write it in like this completely abstract notation, which lets us treat E as a vector space over F. So we can write this as E is a F vector space. If an extension field E of F has is a finite dimensional vector space of F with dimension n, we say that E is a finite extension of degree n over F, and we write E over F is equal to n. So dimension with respect to F of E is equal to the index of E in F, which is, it's weird notation. To indicate the dimension of E over F. Theorem 21.15. Every finite extension field E of a field F is an algebraic extension. Proof. Let alpha be an E. Since EF equals n, the elements 1, a, all the way to a to the n, cannot be linearly independent. Hence, there exists some alpha I in F, not all 0, such that alpha n, an alpha n, plus an minus 1 alpha n minus 1, plus on and on to plus a1 alpha plus a naught is equal to 0. Therefore, p of x is equal to alpha n x to the n plus on and on to plus alpha naught in f of x is a non-zero polynomial with p of alpha is equal to 0. And then bringing back the uniqueness of the modic polynomial, and then creating the respective extension field shows us that like E is an algebraic extension of F. Oh, that's good. I love it. Oh, I love it. Remark 21.16. Theorem 21.15 says that every finite extension field F is an algebraic extension. The converse is false, however. We will leave it as an exercise to show that the set of all elements in R that are algebraic over Q forms an infinite field extension of Q. The next theorem is the counting theorem, similar to Lagrange's theorem in group theory. Theorem 21.17 will prove to be extremely useful in our investigation of finite field extensions. Oh god, yeah, this is really useful. Theorem 21.17. If E is a finite extension of F, and K is a finite extension of E, then K is a finite extension of F, and the index of K in F is equal to the index of K in E times the index of E in F. Proof. Let alpha 1 to alpha n be a basis for E as a vector space over F, and beta 1 to beta m be a basis for K as a vector space over E. We claim that alpha I beta j is a basis for K over F. We will first show that these vectors span K. Let U be equal to U and K. Then U is equal to the sum from j equals 1 to m of bj bj, and bj is equal to the sum from I equals 1 to n of aij ai, where bj is in E and aij is in F. Then, U is equal to the sum from j equals 1 to m of the sum of I equals 1 to n of ij ai bj is equal to the sum of aj just ranging freely over a sub ij, a sub I b sub j. So the mn vectors a sub I b sub j must span K over F. We must show that A sub I, B sub j are linearly independent. Recall that a set of vectors v1, v2, all the way to vn in a vector space V are linearly independent if c1, v1 plus c2, v2 all the way to plus cn, vn equals 0 implies that c1, c2 all the way to cn is equal to 0. Let u be equal to the sum from ij, cij of ai, bj equals 0 for cij in F. We need to prove that all the cij are 0. We can rewrite u as the sum from j equals 1 m times the sum from I equals 1n, cij, ai, bj is equal to u, where the sum from the sum of I, cij, ai is an e. Since the bj's are linearly independent over e, it must be the case that the sum from I equals 1 to n of cij of ai is equal to 0 for all j. However, since the aj's are also linearly independent over F, the aj's are linearly independent over F. So stepping back from the pure reading, what we've done to show that it's linearly independent is we write it as a sum, and then this is a bunch of terms multiplied by bj, with all these in E. And since it's linearly independent and we're talking about linearly independent over F, we're able to bring these out and only worry about this. But then we also use the previous assumption of linear independence to bring it back to 0. So therefore cij is equal to 0 for all I and j, which completes the proof. Oh my god, Elvis. The following corollary is easily proved using mathematical induction. Corollary 21.18. If f sub I is a field for I equals 1 to k, and fi plus 1 is a finite extension of f sub I, then f sub k is a finite extension of f sub 1, and f sub k to f1 is equal to the index of f sub k and f sub k minus 1 times on and on to the index of f sub 2 in f sub 1. Corollary 21.19. Let E be an extension field of F. If alpha in E is algebraic over F with minimal polynomial p of x and beta in f of a with minimal polynomial q of x, then degree of q of x divides degree of p of x. Yes. Proof. We know that degree of p of x is equal to the index of f of alpha in alpha, and degree of q of x is equal to the index of f of beta is in f. Since f is a subset of f of beta is a subset of f of alpha, we know that f of alpha, the index of f of alpha in f, is equal to the index of f of alpha in f of beta times the index of f of beta is in f of alpha is in f. And since the dimension must always be an integer, then we can just simply use basically exact same Lagrange's theorem argument. Example 21.20. Let us determine an extension field of Q containing square root of 3 plus square root of 5. It is easy to determine the minimal polynomial of square root of 3 plus square root of 5 is x to the 4th minus 16x squared plus 4. It follows that the index of Q of square root of 3 plus square root of 5 of Q is equal to 4. We know that 1 square root of 3 is a basis for Q square root of 3 over Q. Hence, square root of 3 plus square root of 5 cannot be in Q square root of 3. It follows as well that square root of 5 cannot be in Q square root of 3 either. Therefore, 1 square root of 5 is a basis for Q square root of 3 square root of 5 is equal to Q square root of 3 square root of 5 over Q square root of 3. And 1 square root of 3 square root of 5 square root of 3 times square root of 5 is equal to square root of 15 is a basis for Q square root of 3 square root of 5 equal to Q square root of 3 plus square root of 5 over Q. This example shows that it is possible that some extensions f of alpha 1 all the way to alpha n is actually a simple extension of f, even though n is greater than 1. Example 21.21. Let us compute a basis for q cube root of 5 plus square root of 5i, where square root of 5 is a positive square root of 5, and the cube root of square root of 5 is a real cube root of 5. We know that the square root of 5i is not in q cube root of 5, so the index of q cube root of 5 square root of 5i in q square cube root of 5 is equal to 2. It is easy to determine that 1 square root of 5i is a basis for q square cube root of 5 square root of 5i over q cube root of the cube root of square root of 5. We also know that 1 cube root of 5 squared is a basis for q cube root of 5 over q. Hence, a basis for q cube root of 5 square root of 5i over q is 1 square root of 5i cube root of 5 squared, cube root of 5 to the 5th I, cube root of 5 to the 7th I, is equal to 5 to the, times the cube root of 5i, or the cube root of 5i. I think that's 3. The numbers are too small for me to read properly. Notice that, is that the 6th root of 5i? Is a 0 of x to the 6 plus 5. We can show this polynomial is irreducible over q using Eisenstein's criterion, where we let p equals 5. Consequently, Q is a subset of Q adjoined 6 root of 5I is a subset of Q adjoined cube root of 5 square root of 5I. But it must be the case that Q adjoined cube root of 6 root of 5I is equal to Q adjoined cube root of 5 square root of 5I, since the degree of both of these extensions is 6. Oh my gosh, okay. That's a lot. That's really cool. But oh my god. Alright. Theorem 21.22. Let E be a field extension of F. Then the following statements are equivalent. 1. E is a finite extension of F. 2. There exists a finite number of algebraic elements A1 to AN in E, such that F is equal to A1 all the way to AN. 3. There exists a sequence of fields E equals F A1 AN, so as a superset of F of A1 to AN minus 1 all the way to F of A1 is a superset of F, where each field F of A1 to F, AI is algebraic over F of A1 AI minus 1. Let me grab some water. Oh my god, my voice is genuinely hurting. I was too hyped for this. Alright, proof. 1 goes to 2. So we're showing that if E is a finite extension, then there exists a finite number of algebraic elements such that E is the extension, the smallest extension field. So let E be a finite algebraic extension of F. Then E is a finite dimensional vector space over F, and there exist bases consisting of elements A1, AN in E, such that E is equal to F A1 all the way to AN. Each A sub I is algebraic over F by theorem 21.15. So 2 goes to 3. Suppose that E equals to F A1 all the way to AN, where every AI is algebraic over F. Then E is equal to F A1 AN all the way to F A1 AN minus 1 is a superset of F A1 is a superset of F, where each field F sum F of A1 is all the way to F AI is algebraic over F of A1 to AI minus 1. Finally, going from 3 to 1. Let E be equal to F of A1 AN to F of A1 to AN minus 1 all the way on to F of A1 F, where each field F of A1 all the way to AI is algebraic over F of A1 AI minus 1. Since F of A1 AI is equal to, my internet just had a moment it looks like, is equal to F of A1 AI minus 1 AI is a simple extension and AI is algebraic over F of A1 AI minus 1, it follows that the index of F of A1 all the way to AI in F of A1 AI minus 1 is finite for each I. Therefore, by our previous inductive theorem, the index of E and F is finite. Oh, okay. Nice. That was a lot. Alright, algebraic closure. Given a field F, the question arises as to whether or not we can find a field E such that every given polynomial P of X has a root in E. This will lead us to the following theorem. Theorem 21.23. Let E be an extension field of F. The set of elements in E that are algebraic over F form a field. So proof. Let alpha, beta, and E be algebraic over F. Then F of A, B is a finite extension of F. Since every element of F of A, B is algebraic over F, A plus minus B, AB, and A over B with B not equal to 0 are all algebraic over F. Consequently, the set of elements in E that are algebraic over F form a field. Corollary 21.24. The set of all algebraic numbers forms a field. That is, the set of all complex numbers that are algebraic over Q makes up a field. Let E be a field extension of F. We define the algebraic closure of a field F in E to be the field consisting of all elements in E that are algebraic over F. A field F is algebraically closed if every non-constant polynomial in F of X has a root in F. The ultimate big boy theorem that we're bringing up is slowly getting ready for the fundamental theorem of algebra. We've talked about this. So theorem 21.25. A field F is algebraically closed if and only if every non-constant polynomial in F of X factors into linear factors over F of X. Proof. Let F be an algebraically closed field. If P of X is in F of X is a non-constant polynomial, then P of X is 0 in F, say alpha. Therefore, X minus alpha must be a factor of P of X, and so P of X is equal to X minus alpha Q1 of X, where degree of Q1 X is equal to degree of P of X minus 1. Continuing this process with Q1, to find a factorization P of X is equal to X minus alpha X minus beta Q2, where degree of Q2X is equal to degree of P of X minus 2. The process must eventually stop since the degree of P of X is finite. Conversely, suppose that every non-constant polynomial in P of X factors into linear factors. Let AX minus B be a factor. Then P of B over A equals 0, and consequently F is algebraically closed. Corollary 21.26. An algebraically closed field F has no proper algebraic extension E. So proof. Let E be an algebraic extension of f, and then f is a subset of E. For alpha and E, the minimal polynomial of alpha is x minus alpha. Therefore, alpha is an f and f is an E. Theorem 21.27. Every field f has a unique algebraic closure. It is a non-trivial fact that every field has a unique algebraic closure. The proof is not extremely difficult, but requires some rather sophisticated set theory. We refer to the reader to 3, 4, or 8 for a proof of this result. We now state the fundamental theorem of algebra, first proven by Gauss at the age of 22 in his doctoral thesis. The theorem states that every polynomial with coefficients in the complex numbers has a root in the complex numbers. The proof of this theorem will be given in chapter 23. Also consult any complex analysis textbook. So theorem 21.28. The field of complex numbers is algebraically closed. 21.2. Splitting fields. Okay, how close are we to the end? Not very close. Oh, I get it. I'm excited, but man, this is going to be a lot. Okay. Splitting fields up here. Let f be a field and p of x be a non-constant polynomial in f of x. We already know that we can find a field extension of f that contains the root of p of x. However, we would like to know whether an extension e of f containing all the roots of p of x exist. In other words, can we find a field extension f such that p of x factors into a product of linear polynomials? What is the smallest possible extension containing all roots of p of x? Let f be a field and p of x is equal to a0 plus a1x plus unknown to plus xn be a non-constant polynomial in f of x. An extension field e of f is a splitting field of p of x. So we'll write E is a splitting field, if it's a splitting field of p of x if there exists a1 an in E such that f is a of p of x. If there exists alpha 1 to alpha n in E such that E is equal to f of alpha 1 to alpha n and p of x, yeah, and p of x is equal to x minus a1 multiplied to x minus an. So basically, it's a splitting field of a certain polynomial if it's almost a semi-simple extension. I'm just going to call this a semi-simple extension because I'm lazy. And we get all the linear factors of the polynomial. So, yeah. A polynomial p of x and f of x splits in E if the product of linear factors in E. So example, excuse me, 21.29. Let p of x be equal to x to the fourth plus 2x squared minus 8 be in q of x. Then p of x is irreducible factors x squared minus 2 and x squared plus 4. Therefore, the field q joined square root of 2I is a splitting field for p of x. Example 21.30. Let p of x be equal to x cubed minus 3 and q of x. Then p of x has a root in the field q joined cube root of 3. However, this field is not a splitting field for p of x, since the complex cube root of 3, negative cube root of square root of 3, or negative cube root of 3, my bad, plus or minus the 6th root of 3 to the 5th I over 2, is not in q adjoined cube root of 3. So basically, we don't have the other linear factors. Alright, theorem 21.31. Let p of x and f of x be a non-constant polynomial. Then there exists a splitting field E for p of x. Proof. We will use mathematical induction on the degree of p of x. If the degree of p of x is equal to 1, then p of x is a linear polynomial, and E is equal to f. Assume that the theorem is true for all polynomials of degree k, with 1 less than or equal to k, less than n, and let the degree of p of x be equal to n. We can assume that p of x is irreducible. Otherwise, by our inductive hypothesis, we're done. By theorem 21.5, there exists a field k, such that p of x is 0, a1, and k. Hence, px is equal to x minus a1 q of x, where q of x and k of x. Since degree of q of x is equal to n minus 1, there's a splitting field E is a superset of k of q of x that contains the zeros of a2 all the way to an of p of x by our inductive hypothesis. Consequently, E is equal to k alpha 2 alpha n is equal to f of alpha 1 all the way to alpha n is a splitting field of p of x. Okay. The question of uniqueness now arises for splitting fields. The question is answered in the affirmative. Given two splitting fields k and L of a polynomial p of x and f of x, there exists a field isomorphism phi of k to L that preserves f. In order to prove this result, we must first prove a lemma. I'm just gonna take a moment to say this is gonna be huge. The concept of a isomorphism that fixes a field, a subfield, is the basis for Galois theory. Which is gonna be a huge thing in 2 chapters. So I will say pay attention. Shh. But first I'm gonna get another sip of water. Yeah, definitely a good idea to stay hydrated. Lemma 21.32. Let phi from E to F be an isomorphism of fields, and let K be an extension field of E, and alpha and K be algebraic over E with minimal polynomial P of X. Suppose that L is an extension field of F, such that beta is the root of a polynomial in f of x obtained from p of x under the image of phi. Then phi extends to a unique isomorphism, E of alpha to f of beta, such that the unique isomorphism it extends to of alpha is equal to beta, and the unique isomorphism agrees with phi on E. That's a lot. Okay. Let me write this all down. So we have that we have an isomorphism of fields E to F. Alright, K is an extension field of E. So I'm going to denote that by inclusion. Extension field of E with minimal polynomial P of X. So I'll also denote P of X with minimal polynomial P of X. Suppose that L is an extension field of F. So we have this extends I1. This is an extension field I2 to a extension field L. Taken from P of X under the image of phi. Suppose that L is an extension field of F such that beta is the root of an equation, root of a polynomial in f of x and P of X under the image. Tains under the image. Okay. Wait. Okay. So we have P of X is in E. So we have such that phi of P of X of beta equals 0. Then phi extends to a unique isomorphism. And this implies that there's a unique isomorphism from E alpha to F beta. Alright, suppose algebraic. Oh, okay. So we have P of alpha is equal to phi of P of beta is equal to 0. So basically, it maps the minimal polynomial, and so we can move the extensions around. We can move the algebraic parts around so that we have f fixed. Okay. Proof. If p of x is degree n, then by theorem 21.13, we can write any element in E of alpha as a linear combination 1, alpha, all the way to alpha n minus 1. Therefore, the isomorphism that we are seeking must be phi bar, alpha plus alpha 1 alpha, plus all in on 2 plus alpha n minus 1 alpha n, is equal to phi of alpha plus phi of alpha 1 beta, plus all the way on and on, 2 plus phi of a n minus 1 beta of n minus 1, where alpha naught plus alpha 1 alpha plus all the way on and on to plus alpha n minus 1 alpha n minus 1 is an element in E of alpha. The fact that phi bar is an isomorphism could be checked by direct computation. However, it is easier to observe that phi bar is a composition of maps that we already know to be isomorphisms. We can extend phi to be an isomorphism from e to x to f of x, which we will also denote by phi, letting phi of a naught plus a1x plus on and on to be equal to phi of a naught plus... Yeah, we basically apply phi to the coefficients of our polynomial. This extension agrees with the original isomorphism phi of e to f, since constant polynomials get mapped to constant polynomials. By assumption, phi of p of x is equal to q of x. Hence, phi maps p of x onto q of x. Consequently, we have an isomorphism C from e of x over p of x to f of x over q of x. By proposition 21.12, we have isomorphism C from e of x over p of x to e of a, and tau from f of x over q of x to f of beta, defined by evaluation at alpha and beta respectively. Therefore, phi bar is equal to tau c sigma negative 1 is the required isomorphism. So what this commutative diagram tells us is that ex goes to that. So this is C. Under alpha and under tau, we have these two transitionatory things, and we can define phi bar as simply we go, because it's an isomorphism, we go in the reverse direction, and then we follow these two. And then obviously it just trivially makes the diagrams commute, and then these are just projections down. And then we leave the proof of uniqueness as an exercise, which we will not be doing because I'm lazy. Because I know what it will ultimately be. It will be the fixing of the base field f, and it will be something about the linear combinations and the fact that we have a linear isomorphism. So anyways, okay. Theorem 21.34. Let phi from e to f be an isomorphisms of fields, and let p of x be a non-constant polynomial in e of x, and q of x the corresponding polynomial in f of x under the isomorphism. If k is a splitting field of p of x, and L is a splitting field of q of x, then phi extends to an isomorphism C from k to L. So proof. We will use mathematical induction on the degree of p of x. We can assume that p of x is irreducible over e. Therefore, q of x is also irreducible over f. If the degree of p of x is equal to 1, then by the definition of a splitting field, k is equal to e, and L is equal to f, and there is nothing to prove. Assume that the theorem holds for all polynomials of degree less than n. Since k is a splitting field of p of x, all the roots of p of x are in k. Choose one of these roots, say alpha, such that e is a subset of e of alpha is a subset of k. Similarly, we can find a root beta of q of x in L, such that f is a subset of f beta is a subset of L. By lemma 21.32, there exists an isomorphism phi bar from e alpha to f beta, such that phi bar alpha is equal to beta, and phi bar agrees with phi on e. Yeah. Now write p of x is equal to x minus a, fx, and q of x is equal to x minus beta g, x for the degrees of f of x and g of x are less than the degrees of p of x and q of x respectively. The field extension k is a splitting field for f of x over e of a, and L is a splitting field for g of x over f of beta. By our inductive hypothesis, there can be an isomorphism, there exists an isomorphism C from k to L, that such that C agrees with phi bar on EA. Hence, there exists an isomorphism C of k to L, such that C agrees with phi on E. Whew, okay. Corollary 21.36. Let p of x be a polynomial in f of x. Then there exists a splitting field k of p of x that is unique up to isomorphism. God, it's worth it, especially for the uniqueness result, but my god, getting there was a thing. Another drink of water. Alright, water's sufficiently chugged. Let's continue. Geometric constructions. In ancient Greece, the classical problems were posed. These problems are geometric in nature, and involve straight edge and compass constructions from what is now high school geometry. That is, we are allowed to only use a straight edge and compass to solve them. The problems can be stated as follows. 1. Given an arbitrary angle, can one trisect the angle into three equal subangles using only a straight edge and compass? 2. Given an arbitrary circle, can one construct a square with the same area using only a straight edge and compass? 3. Given a cube, can one construct the edge of another cube having twice the volume of the original? Again, we are only allowed to use a straight edge and compass to do the constructions. After puzzling mathematicians for over 2,000 years, each of these constructions was finally shown to be impossible. we will use the theory of fields to provide a proof that such solutions do not exist. Oh yeah, this is crazy. It is quite remarkable that the long-sought solutions to each of these three geometric problems comes from abstract algebra. First, let us determine more specifically what we mean by a straight-edge compass, and also examine the nature of these problems in a bit more depth. To begin with, a straight edge is not a ruler. We cannot measure arbitrary lengths with a straight edge. It is merely a tool for drawing a line through 2 points. The statement that the trisection of an arbitrary angle is impossible means that there is at least one angle that is impossible to trisect with a straight edge and compass construction. Certainly, it is possible to trisect an angle in special cases. We can construct a 30-degree angle, hence it is possible to trisect a 90-degree angle. However, we will show that it is impossible to construct a 20-degree angle. Therefore, we cannot trisect a 60-degree angle. So constructible numbers. This I actually know shamefully little about, so I will be taking more intensive notes than usual. So take that. A real number alpha is constructible if we can construct the line segment of length alpha in a finite number of steps from a segment of a unit length by using a straight edge and compass. Okay. The set of all constructible real numbers forms a subfield F of the field of real numbers. This is just a subfield. Proof. Let alpha and beta be constructible numbers. We must show that alpha plus beta, alpha minus beta, alpha beta, and alpha over beta for beta not equal to 0 are also constructible numbers. We can also assume that both alpha and beta are positive with alpha greater than beta. It is quite obvious how to construct alpha plus beta. Just add them, like tip to tail, or like reverse them. To find a line segment with length alpha beta, we assume that beta is greater than 1 and construct the triangle in figure 21.38 such that the triangles delta ABC and delta ADE are similar. Since a over 1 is equal to x over beta, the line segment x has length alpha beta. A similar construction can be made if beta is less than 1. We will leave it as an exercise to show that the same triangle can be used to construct alpha over beta for beta not equal to 0. Oh my gosh, okay. Number 21.39. If alpha is a constructible number, then the square root of alpha is a constructible number. Proof. In figure 21.40, the triangles delta ABD, delta BCD, and delta ABC are similar. Hence, 1 over x is equal to x over a, or x squared is equal to a. Yeah, okay. By theorem 21.37, we can locate in the plane any point P equals P over Q that has rational coordinates P and Q. We need to know what other points can be constructed with a straight edge and compass from points with rational coordinates. So lemma 21.41. Let F be a subfield of R. Let me clear my voice first. If a line contains 2 points in F, then it has the equation ax plus by plus c equals 0, where a, b, and c are in F. 2. If a circle has a center, at a point with coordinates in F, and a radius that is also in F, then it has the equation x squared plus y squared plus dx plus cy plus f equals 0, where d, e, and f are in F. Proof. Let x1, y1, and x2, y2 be points on a line whose coordinates are in F. If x1 equals x2, then the equation of the line through the points x minus x1 equals 0, which has the form ax plus by plus c equals 0. If x1 is not equal to x2, then the equation of the line through the 2 points is given by y minus y1 is equal to y2 minus y1 over x2 minus x1, x minus x1, which can also be put into the proper form. This is just like basic middle school, like late elementary algebra. To prove the second part of the lemma, suppose that x1, y1 is the center of a circle with radius r. Then the circle has the equation x minus x1 squared plus y minus y1 squared minus r squared equals 0, and the equation can easily be put in the appropriate form. Starting then with the field of constructible numbers f, we have 3 possible ways of constructing additional points in R with a straight edge and compass. 1. Define new possible points in R. We can take the intersection of 2 lines, each of which passes through 2 known points with coordinates in F. 2. The intersection of a line that passes through 2 points that have coordinates in F, and a circle whose center has coordinates in F with a radius of a length in F will give new points in R. 3. We can obtain new points in R by intersecting 2 circles whose centers have coordinates in F and whose radii are of lengths in F. The first case gives no new points in R, since the solution of 2 equations is the form ax plus by plus c equals 0 having coefficients in F will always be in F. The third case can be reduced to the second case. Let x squared plus y squared equal plus d1x plus e1y plus f1 equals 0, and x squared plus y squared plus d2x plus t2y plus f1 equals 0, f2 equals 0. Be the equations of the two circles, where di, ci, and fi are in f for I equals 0, I equals 1, 2. These circles have the same intersection as the circle x squared plus y squared plus d1x plus e1x plus f1 equals 0, and the line d1 minus d2x plus e2 minus e1y plus f2 minus f1, 0. The last equation is that of the chord passing through the intersection points of the two circles. Hence, the intersection of two circles can be reduced to the case of the intersection of a line with a circle. Consider the case of the intersection of a line with a circle. We must determine the nature of the following solutions: ax plus by plus c equals 0, and x squared plus y squared plus dx plus ey plus f is equal to 0. If we eliminate y from these equations, we obtain an equation of the form ax squared plus bx plus c equals 0, where a, b, and c are in f. The x-coordinate of the intersection points is given by a famous quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac over 2y, and is in f square root of a, where square root of alpha, where alpha is equal to beta squared minus 4ac is greater than 0. We have proven the following lemma. Lemma 21.42. Let f be a field of constructible numbers. Then the points determined by the intersection of lines and circles in f lie in the field f of square root of alpha for some alpha in f. Theorem 21.43. A real number alpha is a constructible number if and only if there is a sequence of fields q equals f0, subset f1, subset all the way to fk, such that f of I is equal to f of I minus 1, square root of alpha I, with alpha I in fi and alpha in fk. In particular, there exists an integer k greater than 0, such that q alpha, the index of q alpha in q, is equal to 2 to the k. Proof. The existence of the fi's and the a sub i's is a direct consequence of lemma 21.42, and of the fact that f sub k of q is equal to f sub k minus 1 is times f sub k minus 1, f sub k minus 2, all the way on and on, which gives 2 to the k. Corollary. The field of all constructible numbers is an algebraic extension of q. As we can see by the field of constructible numbers, not every algebraic extension of a field is a finite extension. Doubling the cube and squaring the circle. We are now ready to investigate the classical problem of doubling the cube and squaring the circle. We can use the field of constructible numbers to show exactly when a particular geometric construction can be accomplished. First, doubling the cube is impossible. Given the edge of a cube, it is impossible to construct with a straight compass the edge of a cube that has twice the volume of the original cube. Let the original cube have an edge of length 1, and, therefore, a volume of 1. If we can construct a cube having a volume of 2, then this new cube would have an edge of length cube root of 2. However, cube root of 2 is a 0 of the irreducible polynomial x cubed minus 2 over q. Hence, q adjoined cube root of 2, q is equal to 3, which is impossible, since 3 is not a power of 2. Squaring the circle. Suppose that we have a circle of radius 1. The area of the circle is pi. Therefore, we must be able to construct a square with sides square root of pi. This is impossible since pi and consequently square root of pi are both transcendentals. Therefore, using a straight edge and compass, it is not possible to construct a square with the same area as a circle. Trisecting an angle. Trisecting an arbitrary angle is impossible. We will show that it is impossible to trisect a 20-degree angle. Consequently, a 60-degree angle cannot be trisected. We first need to calculate the triple angle formula for the cosine, which it's triple angle formula. I'm just going to read off the beginning and the ends of the formula. Cosine of 3 theta is equal to 4 cosine cubed theta minus 3 cosine theta. The angle theta can be constructed if and only if alpha equals cosine of theta is constructible. Let theta be equal to 20 degrees. Then cosine of 3 theta is equal to cosine of 60 degrees is equal to 1/2. By the triple angle formula for the cosine, 4 alpha cubed minus 3 alpha is equal to 1/2. Therefore, alpha is a 0 of 8x cubed minus 6x minus 1. This polynomial has no factors in zx, and hence is irreducible over qx. Thus, q alpha, the index of q alpha in q is 3, and a cannot be a constructible number. Oh my gosh, okay. That was a lot. This chapter is bulky. And even the exercises are still bulky. Well, I'll read the historical note and then grab some coffee and then I'll get ready. Algebraic number theory uses the tools of algebra to solve problems in number theory. Modern algebraic number theory began with Pierre de Fermat. Certainly, we can find many positive integers that satisfy the equation x squared plus y squared equals z squared. Fermat conjectured that the equation x to the n plus y to the n equals z to the n has no positive integer solutions for n greater than or equal to 3. He stated in his margin of the copy of Latin translation Diophantus Arithmetica that he had found a marvelous proof of this theorem, but that the margin of the book was too narrow to contain it. Building on the work of other mathematicians, it was Andrew Wiles who finally succeeded in proving Fermat's last theorem in the 1990s. Wiles' achievement was reported on the front page of the New York Times. Attempting to prove Fermat's last theorem have led to the important contributions to algebraic number theory by such notable mathematicians as Leonhard Euler. Significant advances in the understanding of Fermat's last theorem were made by Ernst Kummer, and Kummer's student, Leopold Kronecker, became one of the leading algebraists of the 19th century. Kronecker's theory of ideals and the study of algebraic number theory added much to the understanding of fields. David Hilbert and Hermann Minkowski were among the mathematicians who led the way in this subject in the beginning of the 20th century. Hilbert and Minkowski were both mathematicians at Göttingen University in Germany. Göttingen was truly one of the most important centers of mathematical research during the last 2 centuries. The large number of exceptional mathematicians who studied there included Gauss, Dirichlet, Riemann, Dedekind, Noether, and Weil. Andrew Weil answered, Weil, not Weil. Oh my gosh. Andrew Weil answered questions in number theory using algebraic geometry, a field of mathematics that studies geometry by studying commutative rings. From about 1955 to 1970, Alexander Grothendieck dominated the field of algebraic geometry. Pierre Deligne, a student of Grothendieck, solved several of Weil's number theoretic conjectures. One of the most recent contributions to algebra and number theory is Gerd Falting's proof of the modern Mordell-Weil conjecture. The conjecture of Mordell and Weil essentially says that certain polynomials p of xy and z of xy have only a finite number of integral solutions. Okay. Reading questions. What does it mean for an extension field of E to be f to be a simple extension of F? So for this, what we do is we let F be embedded in E, and we basically say that there's some E such that the smallest field of F that contains A in E is equal to E itself. That makes the extension simple. What is the definition of the minimal polynomial of element A and E, where E is an extension of F and alpha is algebraic over F? So it is the polynomial of minimal degree, the mnemonic polynomial of minimal degree, px in f of x, such that p of alpha is equal to 0. Describe how linear algebra enters into this chapter. What critical result relies on a proof that is almost entirely linear algebra? So it's the proof of basically the tower of fields. So it's if E, the notation they would use would be F subset of E is a subset of K. We have that the index of K in F is equal to the index of K in E, my throat, times the index of E in F. Oh my gosh, okay. I don't know if I necessarily want to do the problems, considering my throat is having a bit of a time. Describe how, in linear algebra, the proof of that isn't like entirely linear algebra. What is the definition of an algebraically closed field? So an algebraically closed field is a field such that if you take any polynomial in that, the polynomial factors into elements in the field. What is the splitting field of the polynomial p of x? The splitting field is, in a sense, the smallest field such that p of x factors into linear factors. Yeah, okay. I'll probably do some exercises, but it will be chill. I'm not doing all of these, because especially, don't know if you're hearing my voice. My body was not prepared to read that much linear algebra, or that much abstract algebra. So we'll probably do a short session of math, of problems in that case. Before then though, to get my throat some well-deserved rest. Intermission time. Alright, I'm back for probably just a small bit more math until I end the stream for now, just so that I can like rest my voice a little bit. So, okay, show each of the following numbers algebraic over Q. Okay, actually, I can try this. So, square root of 1/3 plus square root of 7. So we want this to be equal to x, right? So we get that 1/3 plus square root of 7 is equal to x squared. Also, we're doing it over Q. So we need to subtract to get square root of 7 is equal to x squared minus 1/3. To get 7 is equal to x to the 4th. Let me think. We square it, yeah. To get x to the 4th minus 2/3 x squared plus 1/9. And then we subtract by 7 on both sides to get x to the 4th minus 2/3 x squared minus what's 9 times 7? You know, okay, I'm gonna be lazy. 7 minus 1/9 is equal to 0, and this will be our minimal polynomial. It's monic in its leading term, and we specifically designed it to so that over Q, x will be the numbers to this equation is equal to 0. By just like expanding it out and doing our normal rules of arithmetic. And this will functionally be the case for like any such polynomial with like radical stuff underneath. Okay. Find a basis. Oh god, no. Okay, show the splitting field. Oh, what is going on with my internet? Oh, that's not good. Okay. Oh, this internet. Oh no. Okay. Show that the regular n-gon is not constructible. Prove that the cosine of 1 degree is algebraic. Gonna cube be constructed with 3 times the volume of a given cube. Alright. Oh no. So prove that. Alright, a lot of these are just like. Also, obviously, q adjoin root 2 is not isomorphic to q adjoin root 3. I mean, this is interesting, but like, eh. Let's prove z of x over x cubed minus 2. Prove that's a field. I mean, I'm actually wondering about this. So, proof, alright, z of x over x cubed minus 2. X cubed minus 2. So we have a plus bx plus cx squared plus dx cubed. We apply our standard procedure. Like, intuitively, I'm thinking it wouldn't be a field. I'm just wondering how I would justify it. So we want to find a polynomial. Okay, how does x cubed minus 2 work? So like the x cubed minus 2. So we have is equal to x x plus x so is equal to 0. It gives us x cubed is equal to 2, which gives us that x is equal to the cube root of 3. And I'm thinking because the cube root of 3, we also have or the cube root of 2. The cube root of 2 has 3 possible values. Oh, my voice, give me a second. Oh gosh, I'm too tired for this. I don't want to be computing specific examples right now. Let me see if there's, I want to find something like relatively interesting because like, it sounds kind of mean, but like, I really don't like a lot of these problems. Like, because for me, I really enjoy problems more so about like general proof methods. Like in the vector space example, I didn't really do much specific stuff in there, as I more so did just general things. Like even constructing like a functor in a sense. It would probably be a functor from like the category over something, but I'm not entirely worried about that. But like, yeah. Alright, should that cube beta be transcendental? It is kind of disappointing. But like, I'll probably just be doing like one problem because I'm just not interested in all this. This just ain't for me. Because like when we get to Galois theory, there are many more specific examples. It sadly does fall into a lot of that like computation based stuff, which I don't really vibe with that much. But anyways, what I'll do is, okay, let alpha and beta be transcendental over Q. Prove that either alpha beta or alpha plus beta is also transcendental. Oh gosh, it's something like, man, gosh, I don't want to have that disappointment, but I'm just not feeling any of these exercises right now. Because, yeah, you know what? Screw it. I'm not doing this for homework. I'm doing this as a self-passion project. I'm not feeling this right now. I'm doing this later. Although I will suggest, especially if you're watching this, because I'm not doing any examples and you watch for the problems somehow usually, I would suggest like doing these problems on your own. If you're watching this on the YouTube video, in the description, there is a link to this textbook, because this textbook is free online and like hosted by its authors legally. So like, get it, use it, study it. And also, these are first course in abstract algebra. Oh, I've actually heard of a lot of these. Yeah. Well, it's funny how many of these are literally geometric construction things. But anyways, yeah, I guess cutting this off like surprisingly more early than normal. I'll just say my normal. In of a nice